Hello everybody and welcome to my new YouTube channel. My first YouTube channel at all and also my first YouTube video. With a fancy name DSP Corner, which stands for Digital Signal Processing Corner. Yeah, I was very creative. I didn't find a better one, but the name is already indicating the types of videos that I'm going to upload here. Videos about digital signal processing, especially for beginners. I'm trying to upload short small videos where I'm talking about a small problem from the field of digital signal processing, but on an entry level of difficulty. So my first video is, in my first video I'm going to talk about how to plot a sine wave in GNU Octave. Plotting a sine wave is a very basic problem in signal processing, and I'm using here GNU Octave as development environment and scripting language. Octave is similar to MATLAB, but it's open source and free. For sure you can use every other language that you prefer. I personally prefer Python because I think it's much more powerful. But for beginners I think it's easier to follow the content of the video when I'm using Octave, because then they don't have to deal about the syntax of the language and can focus more on the content. So yeah, then let's start by first typing 3 lines of code that you will see often in MATLAB or Octave scripts at the beginning, especially if the function is a main function or if it's a standalone script. It's the clear all command, which clears all the variables that are maybe already set. Close all, which is closing all the windows that are maybe already opened. And CLC, which is cleaning or clearing the command window here. Okay, so we want to plot a sine wave. A sine wave is a continuous waveform oscillating on a specific frequency. And because we are on a computer, we are only able to create digitized signals, meaning that we don't have a continuous signal, we have digitized specific separated sample values. And so these sample values are related to a sampling frequency that we have to define for our signal generation and plotting. So let's define a sample frequency, which is called fs, and let's say we take 300 kilohertz. It's okay if we do it a bit higher. And then we have to define our signal frequency of our sine wave that we want to, or that we are going to create. So here's one big point. We have the Nyquist Theorem that tells us, okay, our sampling frequency should be or has to be twice as high as our signal frequency. So let's say we have a signal frequency of 150 kilohertz, then our sampling frequency 2 times our signal frequency has to be at least 300 kilohertz. So this means the lowest frequency here could be 150 kilohertz. But the problem is, if we are at the Nyquist limit, then we only have 2 sample values per period of the signal. So normally to get smooth plots, you would set the sampling frequency several times higher than your signal frequency. Let's say I'm going here to take a signal frequency of 10 kilohertz, which is 30 times lower than the sampling frequency, giving us nice smooth plots, because then for every period we have 30 samples. Okay, so now we have our signal frequency, the frequency where our sine wave is oscillating, and then we can also generate a small helper variable, which is the delta between the several sample values, and this the spacing between the sample values is the inverse of the sampling frequency. So 1 divided by fs, our dt. Next we have to define the duration of our signal. So we call it t duration. This is the length of our signal when we're generating it. For example, we could generate a sine wave that is oscillating for 1 second, for 1 hour, for 1 year. So, but we will make a short but long enough signal, let's say 1 millisecond. So now we have the basic parameters for our digital signal. We have the sampling frequency. We have our signal frequency where our sine wave is oscillating on. And we have the signal duration of 1 millisecond. To plot or generate our signal, we now have to create a time vector. Let's call it twec. This time domain vector starts at 0 and is incremented by our delta t, because the time spacing between two sample values is delta t. So our increment is, and we are incrementing from 0 to our signal duration. And now a bit confusing, we are subtracting again one sample. This is because we start at 0 and go up to n minus 1. This is this here. If we would start at 1, we would go, if you in a math sense, you would start counting from 1 to n, but if you start counting from 0, then you would go up to n minus 1. This is why we subtract here one sample. So now we have our time domain vector, and now we need the according amplitude values of our sine wave to this time domain vector. Let's call our sine wave x, and there's the sine command, and now we have to implement 2 times pi times our signal frequency, our oscillating frequency, times our t vector. This is it. This is our sine wave. 2 times pi times oscillating frequency times our signal vector. What now is happening is our sine function will be evaluated on every timestamp inside our t vector. 0, dt, 2 times dt, up to the duration of the sine wave. Okay, so now we're going to plot our sine wave. Therefore we create a plot window, which is the figure command, and then we use the plot function to visualize our result. And inside the plot function we plot our time vector against our amplitude values. This is why we pass as first argument our time vector to the function, and our second argument are our amplitude values, our y values. So it's x versus y. Then we name our axis. We have an x-axis, which is the time. So we give it a name like time in seconds. And we have our y-axis, which is presenting our amplitude values. Let's say in volts. It's okay. Volts is okay. Then we also can add the grid on command, which is giving us some vertical and some horizontal and vertical lines inside our plot. It looks nicer. Okay, and then we can fire up everything. Let's check it. So with our sampling frequency, 300 kilohertz. We have our oscillating frequency of our sine wave, which is 30 times lower, to produce nice and smooth plots, because then we have several samples per period, which is 10 kilohertz. We have an overall duration of our signal of 1 millisecond. We have generated our time domain vector because we need it for our sine function to evaluate it at every time instance. And then we plot our time vector against our signal amplitudes. And now we're firing it up. So window is opened and I have to switch over here to show you it. And here it is. So here is our sine wave plot. Quite nice. So what do we have here? We have here our x-axis, our time axis, time in seconds, and as we wished, it goes from 0 up to the overall duration of 1 millisecond. Our y-axis, the amplitudes of our sine wave, goes from -1 to 1, because this is the standard sine wave range. And here we have our oscillations. Yeah, so as you can see, it's quite easy to plot such a wave in Octave. And also our grid lines here, our horizontal and vertical lines, give the plot a nicer look. So yeah, that's all. Quick and dirty video about how to plot a sine wave in GNU Octave. I think you should be able to follow these instructions. I will upload the code together with the video that you can play around with it. I will also attach the links for downloading this development environment. And yeah, then we see us in the next video. Bye bye.